Hello, my name is Jared Skeens and welcome to the Zoom room. Today I would like to cover Pure Maths 1, Functions, Part 2, the inverse function. Now, as we progress through these parts of functions, you should watch them in order. I do try to put them in order as they begin to blend together and correlate with other parts. So we're going to see that as we get into this particular lesson, that the inverse function is going to start blending already with what we've learned in functions, such as composite functions, and it will also start blending into other things that we learned back in the quadratics unit. So as you go along, you want to pay attention to not just the skill of how to do that particular topic, but you also want to pay attention to things that maybe I mentioned about how it correlates or connects with other topics within this unit or within other units, because that correlation is going to be important for you. When I write a question on the board, I am abbreviating the Cambridge instructions a little bit so that it fits on the board, so it's not going to look exactly as you see it in the Cambridge question. So here we're talking about an inverse function. Now, one of the things that I want to mention is when you're looking at an inverse function Cambridge question, often with it will come a question with respect to the domain or the range of the inverse function. Now, I will just briefly mention about, or basically address, the domain statements, but only in respect to their original function. When it comes to the inverse function, domain and range, I will have a separate video later down in a future part, because I feel like you kind of need to understand these concepts first. Then when we get to that domain and range, we can then apply those to the different things, how they apply to composite functions, how they apply to inverse functions, the relationship of a regular function with its inverse. So let's look. In this video, I'll only focus on the skill of finding the inverse function and how the inverse function question is correlated with other topics within the function unit and also with quadratics. But the domain and range part, I will wait for a future video. So if you're looking at question types and you're wondering why I'm not addressing the domain and range right now, it's because I'm waiting for a later video for that. So just keep watching the videos in order, and hopefully eventually it will tie everything together that you need. So like I said, Cambridge does a really good job at correlating information. So I'm trying to keep our topic a little bit narrow on this particular one and look at more how it correlates with past material, but we will get to the domain and range in a future video. So first off, you need to, again, pay attention to notation. Notation is not the math, but it tells you what you're supposed to do. So when you see this function of x with what looks like a -1 exponent, that is your notation that you're finding the inverse, okay? Now that is not really an exponent. It's a superscript of the function. It does not function like an exponent does in algebra. For example, in algebra, if you have x to the -1, it becomes 1 over x. That is not what this notation means. Do not treat it as an exponent. That's a mistake that I notice that some people do. It's not the meaning. What the meaning is that the function that you're going to find is actually the opposite of the original function. And you'll be able to see that better once we've actually found the inverse function. So a test that you could do, you don't actually have to do it, you know, it's not something that you need to do to double check it, but if you wanted to, you could, and that is a function of its inverse, or even if you put the inverse function first and then the regular function, the function and its inverse cancel out, and you're just going to end up with x. So this is one way of testing to see if these two things are actually inverses of each other, is to do this composite function of the function and its inverse, and you should come out with x. Okay, so we'll look at that here after our one of our examples here. So here we and this right here is our two steps that we do to find the inverse. Now, hopefully you already learned this in IGCSE material. In IGCSE, you do have to be able to do basic function evaluation. You need to be able to do composite functions, and you also need to be able to find the inverse. So there should be an element of review here. And so what I think is going to be you know, the more important as we go through the examples is the correlation than just the skill itself. But this is a good review. So here we have f of x and g of x. Okay, so f of x equals 3x minus 2. Now I'm just addressing the domain statement. We're not going to talk about domain and range so much in this video, but the domain statement is provided. And what this means is x can be any number from the set of reals. Any real number is allowed to be plugged into this function. You should also recognize this function as a linear equation, like y equals mx plus c. Then you have this g of x function, and notice it's a fraction, and they give the domain statement that x can be any number from the real set, except x cannot be 1. And the reason why x cannot be 1 is because it's a fraction. And if you put 1 into this, 1 minus 1 is 0. You can't divide by 0, and that's why 1 is eliminated from the domain. So these are just domain statements provided that fit these particular functions. Like I said, later, when you have to start finding domain and range, I'll address that in a separate video, but they do start asking for that with inverse functions. But I'm going to set that part aside and just deal with the skill and the correlation part. So find expressions for the inverse of f of x and the inverse of g of x. So we'll start with our f of x here. And we have, and I'm going to replace f of x with y. Now maybe I didn't mention this in the beginning, the part 1 video, but f of x can be, anytime you see f of x or g of x, anytime you see function notation, you can replace it with the y. Not every equation is a function, but every function is an equation. Okay, so for example, if you see a y in a circular equation, we saw in the part 1, circles are not functions. You cannot replace the y with f of x. But when you see f of x, you can replace it with a y. Okay, so f of x can be replaced with y, so that we're making it a 2-variable equation. This is just notation here, 3x minus 2. So this is the equation of our function. Now, our first step is to switch the x and y. That's easy step. So our y becomes x, and our x becomes y. Okay, so this is just the first step, switch x and y, and then solve for y. We want to make y the subject of the equation. So to do that, we have to get y by itself. So we're going to add 2 to both sides. So we get, I'm going to put the 3y first because we're going to want the y in front, and then the x plus 2. And then we want to divide both sides by 3. Okay. Now when you get to the end, don't leave your y as a y. Cambridge people who are looking at your math want to see that you recognize this as the inverse function. They don't want to just see that you've identified an equation. So you need to actually identify this as your your inverse function with x plus 2 divided by 3. So restate your y as an inverse function notation, and then you have x plus 2 over 3. Now, remember I said over here that your function and inverse function are opposites. They undo each other, just like add and subtract are opposites, multiply and divide are opposites, radicals and exponents. Those are opposite operations. Well, opposite functions undo what the original function did to the variable x. So if you look up here, to our x, we have a multiply by 3 and a subtract 2. Well, if you look at our x down here, we have an add 2. Well, add 2 is the opposite of subtract 2, and here's a multiply by 3, and here's a divide by 3. So if you were to put this function using composite functions, this one into this one, or this one into this one, well, let's just do it and see really quick. If we put this one up here, we get 3 times x plus 2 over 3 minus 2. The 3's cancel, x plus 2 minus 2. 2's cancel, and what do you know? You just get x. So this is kind of like your test to show that this function is indeed an inverse function of this one up here, and vice versa. They are opposites of each other. So that's the concept of inverse function, and a lot of your question types are going to be involved with finding the inverse function and then correlating that with some other thing that you've learned up to this point. So I'm going to get rid of this, and we're going to continue on with our g of x. Now, notice this one is a fraction, but there's not an x in the denominator. So really, we have no change in the domain. There's no change in the domain because the bottom number is just 3. So it's not possible to get a 0 in the denominator and violate the divide by 0 rule. So our domain for this inverse function just stays all real like this one. Now let's go to our g function. So again, we're going to rewrite it with a y equals 2x plus 3 over x minus 1. First thing that we want to do is we want to switch our x and y. This one might take a little bit more space here. That's okay. X equals. Now notice we have 2 x's. So both of those need to become y. So we switch the x and y. Now we need to make y the subject. We need to solve for y. Here it's a little bit trickier because we have 2 y's. So you're going to have to work it patiently so that you can get those y's combined into one term. So what we want to do is we want to, again, we have fractions in an equation, so we want to multiply both sides by y minus 1 to get rid of this fraction. So what we end up with is x times y minus 1. Here it cancels, and you get just 2y plus 3. Then you're going to want to distribute your x through this parenthesis. So you're going to have to just kind of watch to see where we're going with this. Just follow the math, get rid of the fraction, distribute, so you get xy minus x equals 2y plus 3. Now, at this point, notice that some of our terms have a y in them, and some of them do not. So in order to get our y, the subject, what we want to do is we want to get all the terms that have y in it on one side and the terms that do not have y in it on the other side. Okay, so that means we need to subtract this 2y from over here. Okay, so we get xy minus the 2y equals x plus 3. Now I did a couple of steps together there. I hope you can follow it. So here's the xy. We subtracted 2y from both sides, and it shows up right here, cancels from this side. And this does not have a y in it, the minus x, so we added it to the other side, and then here's the 3. So we have all 4 terms with the y, the ones with y in it. Don't worry about the x. The ones that have y in it on one side, and those that do not have y in it on the other side. Okay, so we're focusing in on the y because we are solving for y. So we need to get the y by itself, and to do that, we need to first of all get our y terms together. Now, I'm going to just erase this little bit so we have some room over here. It's a little tight, but I think we can get it in. We're going to bring this up to here. And what we want to do is we want to factor the y out. Since it's common to those terms, we're going to factor it out. That leaves us with x minus 2 equals x plus 3. Okay? Now that we have the y factored out, now we can divide this x minus 2 that we don't need over to the other side, and it becomes y equals x plus 3 over x minus 2. And remember, when you finish your equation, once you get y by itself, don't forget to put it back into your function notation. In this case, the inverse of g of x. So we have x plus 3 over x minus 2. It does ask you for what value it, or to write the domain statement for this g of x function. In other words, we have a fraction. What value is x not allowed to have? So usually I don't rewrite this real one. In fact, it's not really necessary. What's important is the one you can't use. So by saying that x cannot equal 1 is basically saying you can use anything but 1. So what value do you think we cannot use in this inverse function? Remember, we're dealing with fractions. You can't divide by 0. So if you can't divide by 0, the easy way to figure it out is just set the bottom equal to 0 and solve. You get x equals 2. So when x equals 2, you get 2 minus 2 is 0. You get a 0 in the denominator. So obviously x cannot equal 2. That's going to be the domain statement that goes with it. I'll cover this again when we get to that domain range lesson, but it will be a lot more expansive. And so I think maybe if you're introduced to it a little bit as we go, then when we get to the lesson that focuses on it, maybe you'll be able to catch on to it a little bit better. But a lot of students struggle with domain and range. It is more conceptual. You can make it a little bit algebraic, but a lot of it is really conceptual and connections, correlations and understanding how it works. A lot of times it's only 1 point in the Cambridge question as far as its point value. So some of it is even just recognition. You should be able to look at this right away and say, oh, x can't be 2, it's a fraction, can't divide by 0. So I'm just trying to introduce to you as we go to that domain concept so that you can start developing that part of your thinking in addition to the skill set. Okay, so this is our first example, mainly just finding the inverse functions, and we had one little piece of domain here. So let me set up another question for us. Okay, here's our second example. Do you recognize it? Well, actually we did the composite function back in part 1 when we talked about composite functions. So we actually already did the first part of this, but what I want you to see here is they're taking now an inverse function of a composite. Okay, that's different than finding the inverse of f and the inverse of g like we did in the first example. This is finding the composite first, then doing the inverse of the composite. So because we already did this in part 1, I will go through it quickly just so that you can review your composite functions and see how they're correlated together. So that means we have to put g of x into f of x. So if we put our g into f, we get 3 over 2 times 1 over x plus 2, and then don't forget the plus 1 on the outside. So we're putting our g function, that's the inside, and we're working our way out into the f function, the x for the f function there. Okay, so g gets put into f. So here we have this, and we want to go through this relatively quickly. So we get 3 over, this is 2 over x plus 4 plus 1 equals 3 over 2 over x plus 5. Okay, come back down this way. And remember, we have a complex fraction. We wanted it in this form. So we're going to multiply top and bottom by x on this right here so that we can get a common denominator. That gives us 3 over 2 plus 5x all over x. So here's the 2 plus 5x all over a common denominator of x. Again, pay attention to your major division bar, which separates numerator from denominator. So you invert and multiply. So you multiply by x over 2 plus 5x, and you get 3x over, actually it wanted it with the x term first. So 5x plus 2. So maybe you remember doing that in part 1. Now they're moving forward, and keep this in mind in Cambridge questions when you're dealing with part A, part B, or a part I to part II to III, and then IV. And when you're going through those parts, always keep in mind and look for the connections with what you've already done. Since we already did this in the previous part, you don't have to do it all over again. I'm just doing it now because we're in a different video and I've already erased it from the previous video. So pay attention to that so you're not duplicating your work and taking more time. Part of learning math is learning how to think and correlate. So recognize when you've already done work that applies to the next question. Okay, that's important. It's called linking your questions together. Cambridge really likes to do that. Unless it says in the case where it means it's separate and not related, then you should look for the possible connection. There's definitely the connection in this particular question because we already did that previously. So then you can move from here right into our inverse. So now that we have our composite function, which by the way, this is our f of g of x. Okay, this is our f of g of x, is this. Now we want to find the inverse of our composite. So again, we switch x and y. So we're going to start that over here. So we have y equals our 3x over 5x plus 2. We switch our x and y. So we have x equals 3y over 5y plus 2. So we're going to solve this very similar to the first example where we have a fraction. You have two x's that need replaced with y's. As long as they are the same power, it's not a problem. Where we get into the problem is when they are different powers, and I'll have an example for coming up for that. So we want to get rid of our fraction. We want to multiply both sides by 5y plus 2. So we have x times 5y plus 2 equals, this cancels, and you get 3y. So 5y plus 2 times this, 5y plus 2 times this. Distribute. So I'm going to bring this over here a little bit. So we get 5xy plus 2x equals 3y. Now again, get the y's. We're solving for y. This is our goal. Keep in mind what it is that you're trying to do. So don't get lost in the algebra and just start moving things without thinking about what it is you're trying to do. So we want to get the y's together. So that means this term needs to come over here with this one. This one needs to go to the other side. So what we end up with is 5xy minus the 3y equals a negative 2x. So here's term number 1. This one we don't need. It doesn't have a y in it, so it gets moved over. This one does have a y, so we move it to the left side. That way the terms that have y in it are on one side, terms that do not have y the other side. Now we factor the y out, so we get y times 5x minus 3 equals negative 2x. Then we can divide both sides by this 5x minus 3 so that it cancels out. We replace our y with our function notation. So this is a composite function. The inverse of a composite function equals negative 2x over 5x minus 3. Okay, and notice we are in the form, our a is the negative 2, the b is 5, and the c is negative 3. And we have our form that they ask for. Okay, so this was a little similar to the last one in the sense of you had fractions with 2 x's. It was also correlated with composite functions from the previous video. Okay, so let me set up another question for us to look at. Okay, here's another question for us, and this really gets into the importance of being able to correlate information and also follow progression of the questions that Cambridge gives to you. So not only correlating functions with quadratics, but also making connections between the linked information from part 1, in this case, to part 4. So I put the part I of the question. Here's the original information provided. Here we have a function f of x. You see this quadratic, 2x squared minus 12x plus 7. Of course, the domain can be anything. At this particular point, the domain can be all reals, and there's no fractions in here that cause problems. So as in the part I, you can see this is actually from the quadratics unit. It's taking a quadratic and it's completing the square. But it's starting with a function notation question, whereas your quadratics unit didn't usually start with function notation. So like I said, the two units are interconnected quite well. So it starts with function notation, and it first gives you a quadratic unit type question here, complete the square. Now the part II and the part III actually get into domain and range issues that I will address in a future video. I don't really want to take the time to get into that now, so I skip those. In those two questions, the function up here is changed into g of x, okay? So as we go from I through these parts, this is renamed g of x, okay? So you need to be aware of that. When they give you another function, g of x, pay attention because sometimes they're just restating a previous one. So what you end up getting is g of x equals this 2x squared minus 12x plus 7. And there's a domain statement here that I'm just going to put k for right now. Like I said, we'll talk about the domain issue in a different video. What we want to focus on is this inverse function. Now, if you were to ignore part I, and you're just looking at part IV, and you see find the inverse of g, and so you look above it to find the g function, and the g of x is equal to this quadratic, you might make a very terrible mistake. I see a lot of students do this. They waste a lot of time. They do a lot of math running in circles, and they can't get the answer. Here's the problem. If you switch x and y on this, you take this as the y, so you make that the x, and you get 2y squared minus 12y plus 7. Now, in the previous two examples, we had two x's that turned into two y's. If they are the same power, it's no problem because you can put the terms together and factor the y out. If you try to factor the y out, you're still going to have a y left over. You can't isolate the y in this kind of a format. And so students switch x and y, and then they spend a lot of math going in circles and circles trying to get the y by itself. They're trying to solve for y, and they can't get the y by itself because you have a squared and a first power. And some students literally will do a whole page of work, and finally, eventually, they give up because they get stuck. They just stop. And so pay close attention when you have to take an inverse function of a quadratic. It is imperative. It is very important. If you want to not get frustrated and waste a lot of time, it's very important that you pay attention to this part I first. You need to complete the square so that when you switch x and y, you only have one x that turns into a y. You don't end up with two different y's of two different powers. Okay? So whether they give you a part I to do that or not really doesn't matter. You need to complete the square. But if you already completed the square and all they did was rename the function, but the function is actually the same thing, it means you've already done the work, and it's quite not very difficult then to do this. But if you fail to recognize that connection, both with this and the necessity to complete the square, and whether or not you've actually already done it in the previous part of the question, it's just really frustrating. So trying to save you frustration, a lot of math frustration comes because of not paying attention to things like this. I know it's frustrating when you can't get an answer, but if you're not paying attention, then that can make it worse, okay? So what we want to do is we want to complete the square. So this is a nice opportunity to review completing the square. So let's do it really quickly so we can focus on this part. So to complete the square, notice the 7 does not work. So we move the 7 off to the side, and we want to come up with our magic number that works. But before we do our magic number, we need to get rid of this a term. So we're going to factor it to the front only from these two, not from this. We already got rid of that. So we factor out the 2. Notice it fits our pattern up here, the 2 in front. Minus, this is now a 6. Remember, factoring is dividing, 6x. Here is our magic number that we're looking for. And we have our plus 7 that we moved aside. And then actually this needs to be a minus here. We need to equalize our expression. Notice it's an expression at this point. It's an expression. They're not making it an equation, so we don't have that equal 0 in here. So we moved the 7 over. We divided out the 2. We're ready for the magic number. Remember, the magic number is b over 2 squared. Here's the b, the 6. Negative 6 divided by 2 is a negative 3. Negative 3 squared is 9. Then don't forget, when you equalize it, don't be in a rush to put plus 9 and minus 9. Pay attention to this value in the front. You factored out a 2. That means we've added 9 twice. So we've actually added 18, which means we need to subtract 18 to equalize it. So a good review from quadratics. Now it's ready to factor. 2 times x, here's our minus, and the number right before we did it is negative 3. There's the minus, here's the 3 squared, and 7 minus 18 is a negative 11. Okay, so this k up here will have been a 3, which comes from right here. We'll talk about that later as to why that is. But now that I've completed the square and now can put in our little domain statement, and again, don't worry about that now. So what we want to do now is recognize that our g of x is the same thing as f of x. They've just relabeled it with a different notation. And we want to find the inverse g of x. We can't use the standard quadratic. We don't want 2 y's of different powers. We're going to use this. So here is our y equals 2x minus 3 squared minus 11. This is the same thing, but in the complete the square form instead of the standard form. This is like our vertex form. So now we can switch x and y. This is the important thing to remember when you're doing an inverse function of a quadratic. You must be in this complete the square form. X equals 2y minus 3 squared minus 11. Now it's a lot easier to solve for the y. So you have to be careful, though, to do it in the opposite order of operations. So I need to add the 11 first. So make sure out of all these things, don't divide by 2 first. You have to go backwards through your order of operations. So add 11. So we get 2y minus 3 squared equals x plus 11. So I put this over here since we're solving for y, x plus 11 over here. Now you divide by 2. And now we need to square root to get rid of the square. Don't forget the plus or minus, although you're not going to put both plus and minus. And it has to do again with the domain, which I will explain again in a video. That's why I need a whole video just to talk about domain and range, because there's a lot of little details about it. So basically what you're looking for here as to whether to put the, let's finish this first. So we'll put plus and minus for now. Then we have to add 3. So we need to add 3, but the 3 is outside the radical. Don't put it inside the radical. We've already put the radical. So we add 3 outside the radical, and our y can now be rewritten as our inverse function of g. this is going to be the positive root x plus 11 over 2 plus 3. Now, basically, the simple answer to this as to whether you take the positive or negative, if this says x greater than 3, okay, greater than is in the positive direction. So take the positive root. If this said x less than 3, okay, if it said less than 3, less than is in the negative direction, and you would put a negative in front. You don't put both the plus and minus, and right now don't have time to explain that. It has to do with the domain and range going from a function to an inverse function. So just for now, look at your greater than or less than. Greater than is in the positive direction, less than is in the negative direction. Use that as your guide for now until I can explain it to you a little bit more clearly. Okay, so very important example for us because it correlates back with quadratics, and it's an important correlation because you can't find the inverse without that complete the square. And I really hope you pay attention because I don't want you to get frustrated running in circles trying to figure out how to get the y by itself when you have a y squared and y. It doesn't work. So please pay attention. Hope you're taking notes in your workbook. Okay, so I'll have one more example for us here to finish off our part 2. Okay, here's our last example, but it is also another example that is a good opportunity to see how Cambridge correlates different concepts that you've learned up to this point. So what I have for us here is the first information that's provided. Here's our f of x function equals 2 divided by 3 minus 2x. We see that the domain statement gives us the value of x that it can't be. If you put 3 halves in here, the 2's cancel, 3 minus 3 is 0. You can't divide by 0. So that's the domain statement, what it can't be. And then in part I simply asked you to find the inverse function of f. Well, let's do that before we get looking too far ahead. Let's just go ahead and find the inverse function of f. And we'll do it over here. So remember, this is our y. And we're going to replace our, I'll just write y equals 2 over 3 minus 2x. So we switch x and y. Right? We have a fraction here, so we're going to want to multiply 3 minus 2y to get it out of the denominator, and that gives us with x times 3 minus 2y equals, this cancels 2. If you want to look at it as cross multiplication, you can do cross multiplication, although usually cross multiplication is with ratios, but you can do that. Just clear out your fraction. Then we need to distribute this x through our parenthesis. So we get 3x minus 2xy equals 2. Remember, find all your terms that have a y in it. Well, we only have one. That's okay. And move the ones that don't have a y into it to the other side. Well, I like to keep my y positive, so I'm actually going to move it to this side and move the 2 over here. So if we add the 2xy to the other side, then subtract the 2, we get 3x minus 2. So notice we have 3 terms. I added the 2xy so that it's positive, and I subtracted the 2 so that we have 3x minus 2. I also switch sides of the equation to put the y in front. So I did take a couple of steps in one there. Hope that you can follow that. If you need to do step by step, that's fine. But hopefully if you're in A-level math, you can do a couple of steps at a time. but no problem if you have to go line by line. Now we want the y by itself, so we're going to divide the 2x to the other side and get rid of that. Remember to write your y back into our function notation. So our inverse function is equal to 3x minus 2 over 2x. Okay, now as you move into part II, notice I did not write part II, and that's because it has to do with a composite function. Well, we already did composite functions back in part 1 of our series, and it's not connected with our inverse function. But we already did our inverse function of f, and when we get to part II, it uses the inverse function of f. We also need to find the inverse function of g, and they are put into an equation that needs to figure out this over here. So before we get to interpreting this, let's go ahead and find what is our inverse function of g. I'm going to do that over here so that we can work in the middle when we get to this part here. So our inverse function, this is our y equals 4x plus a. Switch x and y, so this becomes x equals 4y plus a. Now we need to solve for the y, so we're going to subtract the a from both sides, so we get 4y equals x minus a. Again, I'm moving the y to the front since we want it by itself. And we divide by 4 to get the y by itself. And don't forget to write it as the inverse function. In this case, the inverse function of g of x equals x minus a all over 4. Now we get to where Cambridge is correlating our inverse skill from the functions unit back to a quadratics question that we saw at the end of the quadratics unit. Remember what I called the crown jewel question of Cambridge for quadratics, and that is this set of values. Remember, set of values means that you're dealing with inequalities, and we have 2 equal roots. Now be careful. Hopefully what is coming to your mind here, when you set one equation to another, you're going to get 3x minus 2 over 2x equals x minus a over 4. Now let's just say you don't recognize what this means yet, okay? Well, you can find the inverse function of f. Okay, we know how to do that. You can find the inverse function of g of x. We did that. You can set them equal to each other. Hopefully you realize that this is some sort of a solving problem, but we've got 2 variables in it. Okay, let's just see how far we get. So let's assume you forget this correlation for the moment. Keep going, and maybe it will come back to your mind what you're supposed to do. So here again, we can do the cross multiplying here. So we can take 4 times the 3x minus 2, and we can take 2x times x minus a. So that gives us 12x minus 8 equals 2x squared minus 2ax. Now at this point, you should recognize that we just went into the area of quadratics because you see this x squared. As you're working, maybe you don't understand the question completely. Go with what information you have, and as you work things out, things like this should trigger in your mind that, oh, this is quadratics now. So that's going to help you interpret this over here. What does this mean? You're not just in functions anymore. Now we're in quadratics, and to solve a quadratic, you need to put it in exponential order. So our 2x squared comes first. So it's positive. I'll just leave it there, 2x squared. We have this minus 2ax. And we also need to subtract 12. And we also need to add 8. So we're moving it all to the same side, setting it equal to 0. So here's our 2x squared. Here's our minus 2ax. We want to move these over into this direction over here. So we subtract the 12x and add the 8. Now we see that these are actually like terms. They both have x in it. So we have a 2x squared. Take out the minus, factor it to the front. That leaves a 2a plus 12x plus 8 equal 0. So we make this, it's a like term, factor the negative out. You don't need to factor out the 2. There is a 2 common to it, but what's important is getting that negative sign to the front, the 2a plus 12. If you factored out the 2 also, it's not a problem, but for this type of question, I'd just leave the 2 inside and take out the negative only so that these can be positive here, and especially the front one. Doesn't really matter whether that one comes out to be positive or negative. And then we have our x, so we have the x squared term, the coefficient for the x term, and then the constant. Now, hopefully at this point, you see that you're looking for the values of a, meaning we're not solving for x. We don't need the x variable. We need the a. Hopefully you recognize this as the discriminant, which was our last video in the quadratics unit. This is a case of the discriminant. So you can either use the b squared minus 4ac from the quadratic formula, or if you wanted to, you can use the z squared from the magic potion method. But as we saw back in quadratics, it does seem a little bit more direct to use the b squared minus 4ac. Now the trick is this. Do we take b squared minus 4ac greater than 0, equal to 0, or less than 0? Think for a second, which one do you think it is? Okay, now at first glance, some of you are going to focus on the 2, and you're going to say b squared minus 4ac is greater than 0. Now that I'm thinking about it, I wrote this actually without reading it. Actually, I don't think this says, and I might have deceived you a little bit, not intentionally. This probably doesn't actually say set of values. It's probably just saying find the value or values for a. I may have accidentally put set of values. If you see set of values, it's definitely inequality. But actually, here you might say, what 2 means greater than 0? B squared minus 4ac is greater than 0. But the trick to this is it says equal roots. And if the roots are equal, then basically it's one in the same. So when you see equal roots or identical roots or repeated roots, all of those phrases is the same thing as like saying it's tangent. Only touches in one point. It's that one point shows up twice in the algebra. So really be careful. Don't jump at the number 2. Look at what follows it. So this is a little tricky. It's actually one real root that just happens to show up twice. So this is the b squared minus 4ac equals 0. So again, you're not going to see that set of values. It's just going to say find the values for a. So let me just get rid of this side over here so I have a little bit more room. So what we want is our b squared minus 4ac equals 0 because our 2 roots are equal, meaning they're one in the same. So this means one real root. Okay, a little tricky. Interpretation is important. Pay attention to what you're reading. So this is what we want. So let's just practice that again. Here's our b squared, the negative 2a plus 12 squared minus 4 times 2 times 8 equals 0. When you square a negative, it goes away. So that's why I only leave the negative out. I don't pull the 2 out, so I don't have to worry about that. Square the negative. 2a plus 12 squared becomes 4a squared plus 48a plus 144 minus 8 times 8, 64 equals 0. Kind of big numbers. If you need to work it out, 2a plus 12 times 2a plus 12. Don't just square the parts. Exponents do not distribute to add and subtract. Okay, don't make that mistake. You're in advanced math now. Grade 9, yeah, you can make that mistake, but now you're in A-level math. You need to get past that kind of mistake. Don't distribute exponents to add and subtract. You need to do 2a plus 12 times 2a plus 12. So you get 4a squared. 24 and 24 is 48a. 12 times 12 is 144. So we get 4a squared plus 48a. This is a 80, plus 80 equals 0. And it's divisible by 4, so take out that 4, divide the 4 all the way through. So a squared plus 12a plus 20 makes the numbers a lot easier when you recognize that. Don't try to factor the 80 and the 4. It's a long list of factors. Simplify it if you can. Factors of 20, 1 and 20, 2 and 10, 4 and 5, and they have to add up to 12. That's our 2 and 10. So we get an a plus 2, a plus 10 equals 0. So a can either equal a negative 2 or a can equal negative 10. We have our two values, plural, for a. Sorry if I deceived you by putting set of values, but that is a clue. Set of values does imply an inequality. In this case, because we had the equal 0, there's no inequality, which means their instructions will be just find the values for a. That can also be a clue for you that this is not a 2 real root situation. It is really a 1 real root where that same root is just shows up twice, and you can solve for a. This is review of quadratics, but it came out of inverse functions set equal to each other in this equation. So you can see how functions and quadratics are correlated together. So you really need to understand how they work together. Okay, so that brings us to the end of our inverse function video. I hope it's helpful. I hope you took notes on some of those key details that can help you not be so stressed by mathematics. Thank you for joining me. Thank you for listening, and see you again next time for part 3.